Our dynamic universe. The key areas covered will be balanced and unbalanced forces, the effects of friction and terminal velocity, forces acting in one plane only, the analysis of motion using Newton's first and second laws, frictional force as a negative vector quantity, tension as a pulling force exerted by a string or cable on another object. What we will do today is revise Newton's first two laws, use free body diagrams to analyse the forces on an object, and carry out examples on the above. Newton's first and second laws of motion. Newton's first law. An object will remain stationary or continue at a constant velocity unless acted on by an unbalanced force. i.e., if forces are balanced, an object will remain stationary or move at a constant velocity. Newton's second law. Motion can exist without forces, but for change in motion to occur, forces must be involved. So unbalanced forces cause acceleration. We use the equation F equals ma, or unbalanced force equals mass times acceleration, where unbalanced force is in newtons, mass is in kilograms, and acceleration is in meters per second squared. 1 Newton is the unbalanced force that gives a 1 kilogram mass an acceleration of 1 meter per second squared. Force is a vector quantity. This means it has a direction as well as a magnitude. An accelerating object has an unbalanced force, F, acting on it in the same direction as the acceleration. We also call this the resultant force. If an object is not accelerating, then the unbalanced force is 0. Solving force problems. First, we draw a free body diagram showing the forces acting on the object and the direction of its acceleration. Then we deal with one object at a time. However, when objects are tied together, they behave as a single larger object. Use F equals ma, but remember, F is the unbalanced force. Here is a National 5 level example we can look at, where there is a single force and a single mass. A man pushes a trolley of mass 20 kilograms along a flat surface with a force of 40 newtons. If the effects of friction can be ignored, what is the acceleration of the shopping trolley? First, let's draw our free body diagram. So we have our block. Let's make it a little bit smaller than that. We have our trolley. It is 20 kilograms. And it has a force of 40 newtons being applied to it. If we want to work out the acceleration, we want to use our equation unbalanced force equals mass times acceleration. So we have 40, because that's our overall mass there, because we can ignore friction. Our mass is 20 times by acceleration. Rearranging this, we have A equals 40 over 20. So our final answer, acceleration, equals 2 meters per second squared. Here is another National 5 level example, but this time there are multiple forces and a single mass. A guided missile of mass 1,000 kilograms is fired vertically into the air. The missile's rocket motors provide a thrust of 20,000 newtons and there is a drag force of 2,000 newtons. What is the acceleration of the missile? So again, we want to be drawing our free body diagram first. So basic little picture of a rocket just here. And we want to be adding in our numbers here. Our initial thrust is 20,000 newtons. Our drag is 2,000 newtons. And there is actually another force acting downwards. It's the weight of the rocket. So we have W. We know that W equals mg, which is our mass here, 1,000 times gravity, 9.8. We've got 9,800 newtons there. These are all our forces. There are none side to side. It's just vertical movement here. So we want to calculate our acceleration. So our unbalanced force equals mass times acceleration. We've got a few different forces there. We need to find the overall unbalanced force. This is going to equal our 20,000 moving upwards, take away 2,000 as they're in opposite directions, and take away that 9,800 as well. This is equal to 8,200 newtons. We can pop this into our equation. So F equals ma, we've got 8,200. Oh, too many zeros there. 8,200 equals our mass of 1,000 times acceleration. Rearrange that. We get 8,200 divided by 1,000. And so our final answer is 8.2 meters per second squared. Continuing this example, as the rocket rises, its acceleration is found to increase, and we want to state a possible reason why. One of the reasons could be as it rises, fuel is burnt up, so the mass decreases. Another reason could be thinner air results in a reduction in friction. And a third reason could be the value of g decreases, so the weight is less. You want to be learning two of these for the exam. You want to know two of them off the top of your head. Here is an example, but at higher level this time. We've got a single force and multiple masses. A ski tow pulls two skiers who are connected by a thin nylon rope along a frictionless surface. The tow uses a force of 70 newtons and the skiers have masses of 60 kilograms and 80 kilograms. A. What is the acceleration of the system? And B. What is the tension in the rope? Well, first let's draw our free body diagram. We have two skiers. We're just going to represent them as little boxes. We have a rope between the two. And we have a force of 70 newtons. Let's say we've got 80 kilograms here and 60 kilograms just here. We are looking at the acceleration of the system to begin with, so we can use F equals ma. Our force is 70. Our mass, we are adding the 80 plus the 60, and obviously we don't know our acceleration. Rearrange this, we've got A equals 70 over 80 plus 60, which is 140. And our acceleration is 0.5 meters per second squared. So that's part A done. Part B, we want to work out the tension in the rope. Tension is a force and it's caused by this 80 kilogram person on the back. So we can add a little arrow in here and say that this is tension. If tension is a force and F equals ma, we can also say T equals ma. Here, we want to work out T. Our mass is just the 80 this time, and we want to multiply this by the acceleration, which is 0.5, and so it gives us an answer of 40 newtons. Depending on how the question is given, in this case, we just decided that the 80 kilogram skier was behind the 60 kilogram skier. If they were the opposite way around, you would be getting a different answer for this, so it just depends how it's phrased in the question or what little diagram you are given. A block of mass 4 kilograms and a block of mass 6 kilograms are linked by a spring balance of negligible mass. The blocks are placed on a frictionless surface and a force of 18 newtons is applied to the 6 kilogram block as shown. We want to work out the reading on the spring balance. So first of all, we have a diagram just there, but it's always good practice to draw your own little diagram. So we've got a 4 kilogram block joined to a 6 kilogram block, and we've got a force of 18 newtons. We want to use F equals ma, and so we have 18 equals floor plus 6 times bar acceleration. Rearranging this, A equals 18, 4 plus 6 is 10, so 18 divided by 10 gives us 1.8 meters per second squared. However, this is the overall force there. We want to work out specifically the reading on the spring balance. So we know that this, similar to the last question, we can label as the tension, just here. And so we can say that T equals ma. T equals just the mass of the 4 kilogram block this time, because that's the one on this side that's pulling on the spring balance. And, oh, we don't need to put the units in there, do we? So we times this 4 by the acceleration that we worked out, which is 1.8, and so our tension is 7.2 newtons. This is an answer of A. A car of mass 1,200 kilograms pulls a horse box of mass 700 kilograms along a straight horizontal road. They have an acceleration of 2 meters per second squared. Assuming that the frictional forces are negligible, the tension in the coupling between the car and the horse box is, and that's what we want to work out. Just like previous questions, this coupling in the middle is actually our tension. So drawing our little free body diagram, we have our block at the back, we have this tension in the middle, we have the car at the front, and we have a force at the front. So 700 kilograms here, 1,200 kilograms here, and we haven't been given this force, but we have already been given the acceleration. That's 2 meters per second. So in this case, we don't need to do as many steps as last time, as we can just say this tension is equal to mass times acceleration, which is equal to 700. So you're not adding them together, it's just this horse box that's relevant. And we multiply it by 2, and our final answer is 1,400 newtons, which is C. A skydiver of total mass 85 kilograms is falling vertically. At one point during the fall, the air resistance on the skydiver is 135 newtons. We want to work out the acceleration of the skydiver. Let's draw a little free body diagram. We have our skydiver, we have the air resistance on the skydiver, which is 135 newtons, and the other force that will be acting on the skydiver is their weight. We know W equals mg. We can work this out to be 85 times our 9.8, as that's the value of g, and this is equal to 833 newtons. So now that we have our two forces, we can work out our overall unbalanced force, which is going to be 833 minus 135, as they're in opposite directions. This gives 698 newtons, and that's down the way. Using F equals ma, remembering this is your unbalanced force here, we can say 698 is equal to the mass, which was 85, times by the acceleration. Rearrange that, we get 698 divided by 85, which is 8.2 meters per second squared. This is an answer of D. A helicopter is flying at a constant height above the ground. The helicopter is carrying a crate suspended from a cable as shown. The helicopter reaches its destination and hovers above a drop zone. The total mass of the helicopter and crate is 1.21 times 10 to the 4 kilograms. We want to show that the helicopter produces a lift force of 119 kilonewtons. So we first want to draw a free body diagram. I'm not very good at drawing helicopters. We could just represent it as a box if you want to, but it's useful to have just a little picture of what you're working with. So we can have a little tail on it. Oh, this is terrible, isn't it? Here's our helicopter. Looks more like a fish, but that's fine. What we want to do is work out what forces are acting on it. So like with everything, we've got a weight, so that's equal to mg, and we have some lift force here. This is what we want to work out. Our weight is equal to mass times our gravitational field strength, which is 1.21 times 10 to the 4 times by 9.8, which is equal to 118,580 newtons. We can say that this is approximately 119 kilonewtons. Notice this is the number we're going for, and because the helicopter is flying at a constant height, it's not moving up or down, therefore W and F are actually going to be equal. So there's no vertical movement, the weight is equal to the lift, and the forces are balanced. So if we say F equals W, therefore F equals 119 kilonewtons. Let's look at part 2. The helicopter now drops the crate, which has a mass of 2.3 times 10 to the 3 kilograms. The lift force remains constant. Describe the vertical motion of the helicopter immediately after the crate is dropped, and we need to justify our answer in terms of the forces acting on the helicopter. So first of all, if the helicopter drops the crate, we know that there is going to be a reduction in weight. So we can say the weight reduces. as this 1.21 times 10 to the 4 is lost 2.3 times 10 to the 3 kilograms. If our weight is less, that means our unbalanced force is going to be upwards. As before, we had F above our helicopter and W below. If this decreases, then this as a whole is going to move upwards. So we can say because of the unbalanced force upwards, there is going to be an upwards acceleration. So we just described the vertical motion of the helicopter, as in this upwards acceleration, and we justified it in terms of forces. We said the weight reduces, and therefore the unbalanced force upwards. And therefore there is an unbalanced force upwards.